this video, we're going to be reviewing how to predict the products and then correctly balance the chemical equations. So this takes what we've learned already, the balancing the equations, one step further. You also have to make sure that you completely understand the classifications of the different chemical equations. So what I've done is I've put them over here on this board for you. I think I need to move the camera a little bit. We have synthesis, decomposition, single replacement, and double replacement. To be completely successful at this, you're also going to need your reference sheets with the polyatomic ions, as well as your activity series for the single replacements. The ones that will be on the test eventually are going to be the easier ones. This is a first year chemistry class, so as far as the decompositions and the synthesis go, they are going to be fairly straightforward. You'll have two elements that become one compound, or one compound that's binary made out of two elements that then you break down into their smaller parts. But you're going to be responsible for knowing which ones are diatomic and to make them diatomic in those. As far as the single replacement goes, you really have to look and make sure that a metal is replacing a metal that is higher up on the activity series, or the same thing is true for the non-metals, that a non-metal is replacing a non-metal that is higher up on the activity series. The double replacements, in the description on the problem, it will say that a precipitate forms. If a precipitate does not form, then you simply put NR after the arrow. There's no balancing because nothing actually happened. So what we're going to do is a couple of examples. Hopefully this will help you. You can pause and do this as many times as you want. The first thing you have to be able to do is to recognize which kind of a reaction it is first. That's what you should figure out first, and then know where to go from there. So if you look at the four examples that I put on the whiteboard, maybe pause this and decide what kind you think each one is. And so what we're going to have here in the first one is a double replacement. And the reason I know that is I've got two ions that made this compound and then two more ions that made that compound. So silver, if you look on your reference sheet, silver is a +1 charge. Nitrate is a polyatomic ion. Nitrate has a -1 charge. That's why this is the correct formula. Somebody has written it for us. Sodium is in group 1 on the periodic chart. Everything in group 1 on the periodic chart has a +1 charge. And then carbonate, another polyatomic ion, but it has a -2 charge. So the reason that ionic compounds form is because there's a transfer of electrons and everything has to balance out. So these are correct formulas. Now you need to predict the products that are also correct formulas. So what you're going to do, the silver, which is a positive, is going to go with the negative carbonate, and it has to go in the correct proportion. It has to be the correct ratio so that every electron has some place to go. So that means that the correct formula is Ag2CO3. Carbonate is willing to take 2 extra electrons. One silver is only willing to give 1 electron. So you need 2 of the silvers in order to make the correct compound that is silver carbonate. Then you put the other 2 ions together. So sodium is a +1, nitrate is a -1, and that is the correct formula for the sodium nitrate. When you get to this point, you're not done. You have to make sure that everything is balanced because of the conservation of matter. You can't have atoms just suddenly disappear. So we have 1 silver on that side, but 2 silvers on this side. So I put the coefficient out in front, and that balances out the silver, but it messes up the nitrate. And the nice thing about these kind of equations, the polyatomic ions stay together. And so because of that, I can treat them as if they were one thing and just put a 2 there, and now I have 2 of the nitrates, 2 of the sodium. There's 2 sodium, 1 carbonate, and 1 carbonate. That's how you do the double displacements. When you look at this one, this is 1 compound. So the only thing that it can do is to break down into its parts. So magnesium and bromine. Now, bromine is a diatomic molecule. This is on your reference sheet. So you have to put a 2 down here. And luckily, it's balanced. It didn't break up like this because this is the original compound. It broke up like this because bromine is diatomic. And then you make sure that you write the word balanced to show that you just didn't skip that part. You know that it's a balanced equation. This third one is a single replacement. You have a metal, potassium is a metal, it's to the left of the line on the periodic chart, and you have aluminum nitrate. Aluminum is also a metal, to the left of the line. So the potassium is going to come in, hopefully, and bump out the aluminum. It's a single replacement. A metal ion replaces a metal ion, but you have to make sure that this is actually going to happen. So you look at your activity series, and you see that potassium is indeed above aluminum on
the activity series. That means it's more reactive. It's going to actually happen. So now you have to put them together. Well, potassium is a +1 because it's in group 1 on the periodic chart. Nitrate, like the previous problem, is still a -1. So the compound that the two of them are going to make is KNO3. You don't have to write on the test all of this stuff with the charges. I'm just showing you how this works. If you can do that without showing the charges, that's fine. It's going to make potassium nitrate, and then aluminum is by itself. Aluminum is not a diatomic molecule, it's aluminum. So there's no need to do that. And now we have to balance it. So when we try to balance this, we have 1 potassium and 1 potassium. We have 1 aluminum and 1 aluminum. The nitrate, the polyatomic ions, stay together, so you treat it as if it's one thing. Nitrate on this side, there's just 1 and there's 3 over here. So that means I have to put a 3 there as a coefficient. But then that's going to make 3 potassium, so I'm going to put 3 there as well. The last one is going to be a synthesis. I can tell it's a synthesis because it's 2 simple elements. And so we have to kind of figure out, well, how are they going to bond together? Boron is a +3 charge. Fluorine, in this case, is a -1 because of their placement on the periodic chart. So the compound that they're going to make is BF3. And then notice, not balanced. You've got 2 fluorine over here and you've got 3 on this side. You're gonna have to do the whole least common multiple thing, which is 6. So you're gonna put a 2 here, that makes 6 fluorine on this side, put a 3 here, that makes 6 fluorine on this side, but this also changed the amount of boron atoms. So we're gonna put a 2 over here. And that's how you predict products.